Labs ahead of the rest, at least. I think you are. Do you think I'm wrong, do you? All right, maybe you've fallen behind. Your questions were 2 labs ahead early on. Right, okay, so I hope you don't get discouraged and you keep pushing through with the labs, because I think it will become more, well, it won't necessarily become shorter in time because the complexity keeps building, but I think you'll become more and more familiar with the way things are done and what's sort of expected. And I think you'll find more satisfaction out of the later labs, because you'll see that you've actually achieved something. You know, you've created something that you definitely could not have created 10 weeks before. Right. Today, as usual, I want to start with Q&A. Are there any questions about any of the material that we've been working on, any of the lab issues? Who's managed to have a look at these exercises on flip-flops and sequential components? Have managed, right? Right. Flip-flops, you have. Okay. So, look, in previous years, I would have stood up there at the board and worked through the exercises that I'm providing you the solutions for. There was feedback that suggested that it would be more useful just to put these solutions up and allow you to work through them in your own time. Is that true? I guess you don't see the comparisons, so you don't really get to see what it would be like for me to go through them all, but essentially what would be on the board at the end of the story would be what's in the written up in the solutions, right? So when you go through the solutions, do you see how to do the questions or how to answer the questions, how the problem was solved? Any comments? Okay, please don't be shy. There's only, how many of you is there? 8? Yeah, 8 people in the room. It's not like you're going to embarrass yourself in front of hundreds here. Right. Is that the approach you're taking? Does anybody try a different approach? Look at all the starred solutions and then try the ones that are not starred and see whether you can do them or not? All right. I keep mentioning that given that the quiz is a multi-choice quiz, it's not going to be exactly the same as these exercises, because all of these exercises sort of expect you to reach an answer, and some of them are quick and easy to answer, others take far more time. But essentially you'd be going through the same motions with the quiz questions, so it's worthwhile having prepared by going through these exercises, I think. So there are no questions?
I've got a 6.13. We're supposed to make the right implementation with the minimum possible number of 3 input lines. But if I were to expand around W2, it becomes way easier than W1. And I was wondering if there's a way to know that before doing the actual expansion.
Somewhat, yes, but no. There are definitely hints that you can get, but there's no definitive answer to that question, because in the end, if you have n variables, you might have to compare the solution that you get for all n possible variables on their own, right? If you're only expanding around one of them. So it's not a cheap solution. You still might have to do an exhaustive search. But for many of the problems that we... You're welcome. See, that's the problem I had. Maybe, now it's just resting there, so the next person's going to be like you, find it easy. So what problem was it that you were pointing out? 6.13. So that's in the previous problem set, is it?
Yes. It's in the textbook. I'm not sure if it's in the problem set.
What is it? Is it an exercise or not?
Yeah, it's like a problem at the end of the chapter.
Yeah, okay. So that would have to be here. Let's just have a look. No, wrong one. So 6.13 you say. All right. Okay, so is that the one you're referring to, 6.13?
Yeah.
Right. Can you all see that? So the minimum possible number of 3 input LUTs. Whoa, that's tough. Okay, so what do we know about 3 input LUTs?
Takes 3 inputs.
Right.
Every variable.
What can you implement with a 3 input LUT? Well, you sort of already know the answer to some degree, but, you know, in general, any function of 3 inputs, right? What are some functions of 3 inputs that you know about? And as for Shannon's expansion theorem, what are we always trying to do? Yeah, we want to figure out what are the inputs to a mux, either a 2 to 1, a 4 to 1, an 8 to 1, doesn't really matter what size mux, but that will determine how many variables you'll be expanding around, performing the Shannon expansion around, right? So with a 3 to 1 mux, what size, a 3 input lookup table, what size mux can you implement? I hope you're not really this slow when it comes to quiz. Well, 2 is not the name of a mux. Tell me the name of the mux. You mean a 2 to 1 mux, do you? Because it has 3 inputs, right? It has the input that gets selected when one of the inputs is 0, and the other input is the input that gets selected when the selector is 1, right? So a 2 to 1 mux maps directly to a 3 input lookup table. I don't know. Right, there's 3 inputs here and 1 output. S, I0, I0 and I1 are the 3 inputs, and the output here, F, is an output, right? So that maps directly, obviously, to a 3-to-1 mux, which has got 3 inputs and 1 output. This is called a 3-LUT, right? So in the general case, if we have 4-variable function, how many 3-input lookup tables do we need to implement that? So if we're using a single variable to select, right, that's going to be that guy. And then we're going to have the cofactor with respect to not S and the cofactor with respect to S, right? And how large are those cofactors with respect to S and not S going to be? How many inputs are they going to require? How many variables will they have? At most 3, right? Yeah. Without loss of generality, if you use W1 to expand that function around, the cofactors are going to be functions of W2, W3, and W4, right? Okay, so in the worst case, you'll actually need this will be F with respect to S bar, and this is F with respect to S. They're the 2 cofactors. They're going to be coming in here, and we're going to have S up there. So that leaves us with 3 other variables that have to be described there, yeah? So at worst, we're going to need 3 lookup tables to implement any function of 4 variables. So when it says the minimum possible number of 3-input lookup tables, if you're doing better than 3, that's great, right? Okay, so we have our function. What is it? What's the list? Can somebody read it out?
0, 1, 3, 6, 8, 9, 14, 15.
Right. So, okay, so if we have our, and this is W0, well, they're calling them W1, W2, W3, W4, are they? Right, and we have, for our function, 0 is in, so this is 0, and we have 1, and we have 3, and we have 6, 8, 9, 14, and 15, right? So they're the min terms that are in our function. Yeah? So I could write this out as F is not W1 and not W2 and not W3 and not W4, or not W1, not W2, not W3, W4, or, right, not W1, not W2, W3, W4, or not W1, W2, W3, not W4, etc. Right? So where you can potentially get an optimization, potentially, this one's going to be tricky because it's big. There's a lot of factors cofactors there, a lot of min terms. All these guys involve W0 or W1, right? Not W1, sorry. Not W1. And all of these guys involve W1. So there's 4 terms here that involve W1 and 4 terms that involve not W1. Right? These 3 involve not W2, as do these 2. But the other ones here, this guy and these 2, involve W2, right? You agreed with me with W1, so I'm hoping you can see the same thing for W2. So if you look down W2, the first 4 would involve not W2, the next 4 W2, the next 4 not W2, and then the final 4 W2, right? That's just from the truth table and how min terms are then written out. So there's perhaps a little bit of imbalance because we found 3 that involve W2 but 5 that involve not W2, right? As for W3, we've got 2 that involve not W3, another 2, so that's that's 4. So there must be 4 that involve W3, right? And for W4, well, we've got 1, 2, 3, 4. So they're sort of all balanced. But with many functions, if you think back to our lecture, they were usually functions of 3 variables, so it was a little bit more straightforward, and there was at most 8 min terms, and usually it was only 3 or 4 terms that were included. So it was easy to see which terms involved which variables, and you could pick that there were certain terms that didn't involve either variable, but here, because of the min terms, because we're using min terms, it's sort of the same irrespective. So if you were using W1, then the function that we have to map into this lookup table here, which would correspond to the cofactor with respect to W1 bar, would be these two terms here, this term and this term, right? And similarly, for W1, you'd have these 2 terms and these 2 terms included. So you'd still need 3 lookup tables because there's no obvious relationship between the lower half here of the truth table and the upper half of the truth table. Usually you can avoid or eliminate one of these guys by showing that one is the complement of the other, and thereby eliminating it. So if there's a straightforward relationship between these 2 cofactors, then that allows you to simplify things. Now, as for, well, W2, we knew that there was an imbalance in terms of the numbers, so I doubt that the best solution is going to come with W2. With W3, we have these 2 here, which are also replicated down here for not W3. And we have one here when W3 is asserted, and another one when W3 is asserted. And we have down here these 2 where W3 is asserted. So I'm not so sure yet that there is necessarily a relationship between the cofactor with respect to W3 bar and the cofactor with respect to W3. And as for W4, obvious functional relationship. I'd pick W3 probably as the prime candidate, that there might be some gain to be had by optimizing around W3. Have you done the problem?
I did. W2 gave me the one that had a comp.
Really? W2?
But after doing the Shannon, I had to simplify the inside.
Yeah, you'd have to. Right. So you think we should go for W2, do you?
But I didn't know how to know that the fourth one. But at the start, I did W1.
Well, there's no obvious way of knowing it up here because all terms have got some combination. But it may be because we're using min terms at the moment that results. If we were to map this into a Carnot map, then we have 1, 1, 0, 1, 0, 0, 1, 0, and we have 1, 1, 0, 0, and we have 0, 0, 1, 1. Right. Right, so this would be W1, W2, W3, W4. So we could say that F is equal to, so this is not W2, not W3. We have these two here, which are not W1, not W2, W4, and we have these two vertical ones here, which are W2, W3. And finally, we have the two horizontal ones that are here, which are W2, W3, not W4. Does that agree with what you had?
After the expansion or the function?
So just the simplification at this stage.
Oh no, I took the midterm of the function and then I Shannon on W2 and then simplified. So I didn't do simplify beforehand.
We'll get the same result. So that's the same. So if we were given this function, we can see that there's not W2 and not W3 in this term. There's not W2, but there's no, W3 isn't involved in this term. W2 is in this term, and W2 is in this term, right? So out of W2 and W3, W2 would definitely be better because it covers all of these subfunctions or subterms, right? W4 isn't, well, W1 and W4 aren't included in the first term, but they are included in the second term. Only W1 is in the third term, and only W4 is in the fourth term. So it certainly looks from when we simplify the function, or when we simplify the function, that W2 is best to expand around because we have W2 bar in the first two terms and W2 in the second two terms. So that means that if we write this as cofactors, I'm a bit loath to rub off part of what's on the board while we're still going. So I'm going to write that down here. Continuing on down here, we can say that F is equal to W2 bar and the cofactor of F with respect to W2 bar, or W2 and the cofactor of F with respect to W2, which in this case is W2 bar outside of, well, W3 bar or W1 bar W4. And the cofactor with respect to W2 is W1 W3 or W3 W4 bar. Okay, so that would still fit into this model where you have W3, W1, W3, W4, W1, W3, W4 going into both of these 3 input lookup tables, and you'd have W2 coming into this one to select between these 2 cofactors that are coming in, right? Now, as for the complementarity or not, well, this can be rewritten as W3 outside of W1 or W4 bar, right? And, well, indeed it does look like they're complements. So if we apply De Morgan to this, we'd end up with W3 bar or W1 bar and W4, which is what we have here. Can you all see that? So, in that case, what we can do is, it doesn't really matter which one we pick here, they're going to be the same. We can get away with putting, let's say, W1, W3, and W4 in one of these. We don't have to worry about this guy because we effectively have the complement of that coming in here as well. So this input here can be left at 0. That's fine. How would the program look inside here? So what we're saying here is that we don't need to have the cofactor with respect to W2 if we've got the cofactor with respect to W2 bar, because the cofactor of F with respect to W2 is simply the complement of the cofactor of F with respect to W2 bar, right? As we've already shown here. So what only remains here is to determine what should be the program inside those lookup tables. Did you look at that problem at all?
I didn't talk about that.
But that's pretty easily done. So F with respect to W2 bar, the cofactor, is equal to W3 bar or W1 bar W4. So if we have W1, W3, W4, then F of W2 bar is, so it's not W3, so it's 1, 1, 1, 1, or W1 bar W4, so W1 is barred here, and W4 is here and here. And all other entries are 0, right? Is that clear? So that would be the program that would be written into this lookup table here. And as for the program that has to be written here, well, so S is W2. What we want for that guy say this is W2 and that this is FW2 bar and that this is 0, then the function that we want to have here in our mux, which is f, well, when W2 is 0, right, we want the cofactor of f with respect to W2 to be output. So that would be, so you're just copying what FW2 bar is into f. But when W2 is 1, we want the complement of what FW2 bar is. Oh, sorry, I did that wrong. No, that is correct, sorry. So we're assuming that FW2 bar is 0 in these two cases and 1 in these two cases. I got confused with this column. I should just completely ignore that column. We just want 0, 0, 1, 1. So replicate exactly what we see there. And when W2 is 1, then we want the complement of FW2 bar. So it should be 1, 1, 0, 0. Okay? So if W2 is 1 and the output of this lookup table is 0, then we want a 1 coming out here. If W2 is 1 and the output of FW2 bar is 1, we want to output a 0, which is what this is saying here. So when it's 1, we just output a 0. Okay? So they're the two programs that have to be loaded into these two lookup tables, that one here and this one here. Is that clear? Any questions?
So for the first lookup table, you took the one with the W naught as it. If we were to use the W2 without the naught instead, it would still work, right?
You mean if we took the cofactor with respect to W2
Yes.
instead? Yes, of course. If you took the cofactor with respect to W2, then for, that is, what is it? W1, W3, or W3, W4 bar, right? So, when we have W1 being 1 and W3 is 1, so then, right, and W3 is 1, so for these two I'd have a 1 here, and W3 and W4 bar, so when W3 is 1 and W4 is 0, I have a 1 here, W3 is 1 and 1, they are the complements of each other. Right. Can you see that? So it doesn't really matter which one you use, that's true. Although we'd be programmed differently. The program of this lot would be the same. No, sorry. The program of, if you're implementing the cofactor of f with respect to W2, then the program that you've got to put in here is going to be the complement of this f. Because in that case, when W2 is 0, we want the complement of FW2, right? So it would be 1, 1, 0, 0. And when W2 is 1, we want what's in the cofactor of f with respect to W2. All right, I can see some people are bored by this. Are there any other questions? Should we get some air flow in here? Do you need air? All right, it says it's running now. So, let's just take a photo of that. Are there any other questions?
So the rightmost lookup table basically just functions as a mux, but for generality we just say it is technically a lookup table.
Yeah, it is a lookup table, but it's programmed well, in the general case where you have both cofactors
Yep.
coming into it, in that case it's programmed as a mux,
Yep.
in which case it would be 0, 0, sorry, it'd be whatever, yeah, no, it'd be the same as that, and then down here it would be this pattern instead, because you'd have the cofactor with respect to W2 being active
Yep.
when W2 is active, right?
Okay.
So it'd be 0, 1, 0, sorry, this one would be 0, 1, 0, 1.
Yeah.
Yes.
But in this
That's
case,
in the general case, but in this specific case, no,
we didn't
it
have
isn't, because we've only got the one cofactor there. In
Yep.
fact, the third input's always 0, so I'm never going to get the cases where I have ones coming through.
Yeah. Okay.
All good? Right, do you have further questions? It sounds like you do. We've got another 15 minutes.
But it's, so for 7.5, your solution.
7.5,
The
yes.
solution that you gave, I couldn't really understand the second part because it was like during the clock signal, we're supposed to generate divide it to like by 2.
Oh yeah, I remember the question.
Yeah. The one that I came up with was like doing a ripple with the Q to the next flip flop, and that was cut by 2. But you did it with an XOR gate on the second one.
But if you're using a ripple, so is it synchronous or are you using the cues as the clocks?
I'm using the Q's as the clock.
Yeah. Did the question actually ask for a synchronous solution or did it not matter?
I don't think I mentioned.
But if you want to generate clock signals, you want to ensure that they're as accurate as possible, don't you? So this is flip-flop exercises or?
Yes.
Right.
7 flip flops.
Right, 7.5 is it, or 7.3? Oh, no, 7.5, okay. So given a 100 megahertz clock signal, derive a circuit using D flip-flops to generate 50 megahertz and 25 megahertz clock signals. Draw a timing diagram for all 3 clock signals, assuming reasonable delays. Okay, so if you're using a ripple counter approach, which is what you're suggesting to do, right? You don't need an exclusive OR gate, I don't think. Sorry?
No, you don't.
I thought you said you used an exclusive OR gate.
No, I didn't. Your solution did, but I couldn't understand like how I couldn't see.
So I use an exclusive OR gate because you've got to conditionally invert the input, right? Because you don't want to toggle every clock cycle. Right?
I don't quite get what you meant.
You don't get what I'm talking about. Okay. How about I bring it up? That might be a bit easier for me because I don't have to redraw it. Although before I do that, let's just have a look at your solution. So you're proposing to draw something like this. We have toggle flip-flops, clock input, you have a Q output, Q bar for argument's sake, and you're tying that to 1. So you have a 100 megahertz clock coming in here, So what rate's this going to be toggling at?
Oh, yeah,
50. Okay, so this is going to toggle at 50 megahertz. That's correct. And you're proposing then feeding that straight in, or it doesn't really matter whether it's Q or not Q, into a second toggle flip-flop. And tying the input to 1, presumably.
But using a D, so because the question asks us to use a D flip-flop.
Okay.
But to
Well, then you do.
I
So you're using D flip-flop. So how are you getting the toggling happening?
connect the Q1 wire to the D input.
Oh, okay. Yeah, right. Right, so you get 50 coming out here. That's 50. And that's your clock for the second,
Yes.
for the... and again, you're doing Q bar.
Yeah, same thing.
Right, which means that the output here is going to be 25. Right, that's fine. But if we drew that up precisely, you know, here's your 100 megahertz clock. So the drawback is the 100 megahertz. And your 50 megahertz has to take into account the clock to Q propagation delay, right?
Yes.
So, so that I can draw it, let's assume that's it there. Right, and then this is your 50 megahertz, and your 25 megahertz is going to have, for argument's sake, I have to again have the clock to propagation delay in there, and it's going to arguably go up there and then go like that. Correct? So you've got progressive delay on each of the slower clock signals. Whereas the solution I have is synchronous. So that's asynchronous in some sense. It's not a synchronous design because you're using different clocks. Synchronous by definition means you're using the same clock. So let me just go to the solution that I put up. It's this one here. Right. Well, this is the same as your first stage, right? I'm just using an inverter rather than Q bar. Doesn't really matter, you can use Q bar. That's fine. The critical issue is that you're generating the clock, or you're using the same clock to drive both of these flip-flops. So there is a propagation delay here on the 50 megahertz with respect to the 100 megahertz. And this guy, well, I'm using the exclusive OR gate there as a conditional inverter. When Q is 0, it just passes whatever when, call this Q2, it's probably not very well labelled. When this guy's when Q2 is 0, invert whatever that signal is. All right, so looking at this diagram here, when, if I call this Q1 and this Q2 in my design, so we're getting the same 50 megahertz signal, but when Q1 is 0, we're going to pass through that signal, we're going to pass through the Q2 signal, which, for argument's sake, let's assume is 1 in this case, because otherwise I won't get a 1 straight away. Okay, so the 1 would be reinforced, which would mean it's coming at the same time. Maybe this is not such a great example to use this on. If we assume that they all start on 0 at the same time, so Q1 and Q2 both start on 0 in that design, initially the 0 gets passed through, and only when Q1 becomes 1 does the 0 become toggled on the second flip-flop, so there would be a delay. I think my waveform might be wrong. Oh no, I drew it correctly here, actually. Does this make sense? It does.
The delay or
No, not the delay, but it's not going to go high until the period after Q1 is high. Because it's only when Q1 is high that Q2 gets inverted. So this version of Q2 is going to be inverted on the next active clock edge. This is the next active clock edge, right? And since Q is currently 0 and the input from the left flip-flop is 1, it gets inverted, goes high. And so on the next active clock edge here, because Q1 is low, nothing happens. Q2 stays the same, it recycles the 1. But when Q1 is high again, on the next active clock edge, it goes low this time. It's the exclusive OR function. I can't actually draw it there. And I should really have a 1 and a 2 there to make the discussion more useful. You understood this transition here? Right, so this is the Q1 output, right? And so what we're drawing here is the Q2 output. So at this point in time, Q1 is 0 and Q2 is 0. So what's the exclusive OR of 0 and 0? 0, so it stays 0, right? At this point in time, Q1 is 1 and Q2 is 0. So the output is going to be 1, right? At the next active clock edge here, we have Q1 is 0 and Q2 is 1. So it stays at 1. And at this active clock edge, we have the Q1 is 1, Q2 is 1, so the exclusive OR is 0, so it becomes 0. Okay? Does that clarify it? So, okay, there are swings and roundabouts here. The method that you drew has increasing latency on each of these, or phase shift if you like, for each of the lower frequency components. Mine only has the one phase shift or latency, the TCQ delay that we have up here. That's going to be the same for for this stage as it is for this stage, under the assumption that flip-flops are pretty similar. But we also have a 50% phase shift here. But that's not really going to matter. That's really only for the very first few cycles that matters. After that, it's consistent. All right? But both of them are shifted. Oh no, that's not true. Okay. All right. Any other questions? Is this clear to everybody, what we're talking about? No? No? No, not really. No? Yes? Okay. Being a software person, you don't really care about clocks too much, is that right? Sorry? Good. All right. Okay. We might just get on to the lecture because I have sort of a full lecture planned.
If you were to then half the frequency there, would you just add another stage with like a XOR gate?
Yep.
Yeah. Okay. So just keep
Yeah, just keep on building, or you can keep on building. I don't know whether that's the right solution or not, but that one will do it for a synchronous design. In some ways, the other one is simpler because it's the same for every stage.
Yeah.
What happens here, I think that yeah, this one has to be inverted on every clock cycle. I mean, you could put an exclusive OR gate with a one input, with the other input being one on the first stage here, and then every stage would be the same effectively. All right, let's get to the lecture then. Okay, so we made a good start on this lecture the other day, but there's still a lot to be learned on all these points. So we're going to have a look at two further examples this week, or in this lecture. The first example discusses the control for a bus system. And this bus system is used for communicating between a bunch of registers that are listed here. We want to consider the problem of swapping the contents of two registers using a third as a temporary storage unit. So something that you do in software quite regularly and it's quite easy to do, but in hardware it requires a little bit more thought about how it's all coordinated and so on. So I wanted to first discuss how the registers are connected to the bus. So a bus really is just a set of wires that are shared by a number of components that can each read or write, potentially, to or from the bus. And in this case, we have a couple of 2-bit registers as an illustration connected to the bus via these so-called 3-state buffers. That's these triangles here. Whenever you see a triangle that's in a hardware diagram, that's a buffer. So it's like an amplifier, if you like. But these are controlled. They have a third input, as you see on the side, which determines whether or not the buffer is on. Originally, they were called tri-state buffers when they were first conceived, but that's a registered trademark, so everybody calls them 3-state buffers now instead of tri-state buffers. The performance of the functionality is pretty straightforward. When the control signal is low, as far as the output is concerned, it sees an open circuit, so a high impedance input. It's as if the rest of the circuit here is disconnected from this wire. That's what Z basically means, or high impedance means. On the other hand, when the control input is 1, then the output reflects what's on the input wire. So if the input's 0, the output's 0. If the input's 1, the output's 1. So in that way, the is to connect multiple devices together. All the O's can be wired together as long as only one of these three-state buffers is currently switched on. So here we see that the register 1 contents, as stored in these two flip-flops, these 2-bit registers, are connected respectively to the upper and the lower wire of the bus via these three-state buffers. So when R1 out is set high, then the contents of these two flip-flops are written onto the wires of the bus. Now, it's important that we would never assert R1 out at the same time as R2 out, because then what we're doing is wiring together the outputs of several devices. And that's not allowed. You will break things if that happens. Right. Now, as far as the internals of the register are concerned, note that there's muxes on the D inputs. So when this R in line is low, then the flip-flop is just recirculating its own contents in each case. So when R1 in is low, the register is just saving its current state. When R2 in is low, it's saving its state. But when R1 is asserted, when R1 goes high, we see that the uppermost wire is connected then to the D input on the leftmost flip-flop, and it's the lower wire that's connected to the D input of the right bit of R1 in. And so in order to write the contents of the bus into a register, we simply assert the corresponding in signal for that register, and that writes it in. Is that clear? And it writes it in on an active clock edge. Here these are positive clock edge driven flip-flops, so obviously whatever is on these bus wires only gets written in when we have an active clock edge coming along, a rising clock edge. Okay? So we could have some external agent putting something onto the bus, and we could have all registers loading simultaneously what's on the bus. Any number can read simultaneously, but only one can write to the bus at any one point in time. Okay? All good? Okay, then here's our system that we have, and let's imagine that we have at least 3 registers. Then what we want to do is swap the contents of registers 1 and 2 using a third register R3 for temporary storage. So the questions then arise, of course, what are the so-called register transfers? That's a special term in hardware design. A register transfer is what gets written into a register on a clock edge, on an active clock edge. What are the register transfers that are required to effect that swap? Which control signals need to be asserted to put each register transfer into effect? And finally, how should you sequence those control signals so that you get this coordinated activity that's required in order to swap the contents of registers 1 and 2? Okay, so in our particular system, we can think of the register transfers that have to be performed as firstly copying the contents of register 2 into register 3, then the contents of register 1 into register 2, and finally the contents of register 3 into register 1. Okay, and if you follow that sequence of register transfers, then we will have effectively swapped the contents of registers 1 and 2. Okay. So that answers the question, what are the register transfers that we need to be performed? But as for the control signals, well, what do we need to do to put the contents of register 2 onto the bus? Because we only have the bus in order to communicate between registers here. So we have to put the contents of register 2 on the bus. How do we do that? Well, we have to assert R2 out in order to put the contents Well, that is done by asserting the corresponding in wire to be able to write the contents of the bus into that register. So for the first register transfer, we want to perform these two control actions, and for the other register transfers, it's a similar situation. But it's important to understand also that each one has to be, is only completed, if you like. Each register transfer is only completed when an active clock edge comes along, because only then are the contents of the bus actually written into the register. Until then, they're just sort of dangling there on the inputs to the flip-flop or the inputs to the registers. They're not actually being transferred into the flip-flop, right? We need that clock edge for that to happen. Okay, so we assume we're going to have some sort of controller that makes sure that these control signals are going to be asserted at the right time. So apologies for the beamer that seems to have very poor performance down at the bottom edge here. I have tried to get people to fix it, but they haven't seemingly been able to do that. So we've got to have some sort of control circuit that coordinates these control signal inputs to our system. So here's that controller. We assume that at some stage we want to initiate this copy or swap between R1 and R2. Let's assume that that's given by some trigger, let's call it W. And good hardware design sort of expects, or it's not just hardware design, you expect it in everyday communication. In a sort of a command society or in any sort of organization, if the boss tells you to do something, the boss usually expects you to report back when you've done it, right? So the boss knows you can be reallocated to do something else, right? So similarly here, we're going to issue a done signal as a handshake to indicate that that function has now been performed. So let's have a look at how we would design the finite state machine that's going to issue these respective control signals that we have been discussing. So we're going to follow our usual design approach for finite state machines. We're going to define a state A in which, you know, that's the reset state, the stable sleep state, in which we stay until W is asserted, okay? So while W is not 1, we're going to stay in state A. But when W becomes 1, we're going to go into a state B where we want to perform this first register transfer, right? And in order to perform this register transfer, we've already identified that we want to output the control signals R2 out and R3 in. We want to assert those two control signals. Now they're going to remain asserted while the system is in state B. So while we're in state B, the R2 out and the R3 in wires are going to be high. All other wires are going to be low, okay? But the actual transfer does not take place until a rising clock edge occurs with these control signals being asserted, right? Because only then do we get the contents of the bus, which by this stage are the contents of R2, being written into R3. Okay. Our machine, though, wants to do this as quickly as possible, so it's going to do that on the next rising clock edge. And remember that our definition of finite state machines basically is that we follow whatever transition is given on the next active clock edge, the one that's valid. So in our case, irrespective of what W is on the next clock edge, we're going to move into a state C in which we want to perform that second register transfer. And it's only when we enter state C that this very first transfer A similar argument can be applied to this state C, which refers to or relates to the second transfer. In state C, the control signals are asserted to put that register transfer into effect, but it won't actually occur until the next clock edge takes us into step D, writes into register 2, takes us into stage 3 or state 3, in which we want to perform the last of the transfers, namely to copy the contents of register 3 into register 1. So outputting from register 3 and inputting into register 1. And of course indicating that we're done with the transfer. Effectively, that's going to be true on the next rising clock edge, because on the next rising clock edge, what happens is, irrespective of the state of W, we're going to go back into state A, and it's really on that rising clock edge that that final transfer takes place. So in effect, when we issue the signal to start a transfer, there could be up to almost a complete clock period where nothing happens, but at the end of that clock period on the rising edge, we'll go into this state B, right? In state B, we set up the first of these transfers, but it doesn't happen until the next clock edge comes along that also takes us into state C. And so we see nothing happens in that first cycle. In the second cycle, we perform the first transfer. In the third cycle, we perform the second transfer. And in the fourth cycle, we perform the last transfer that's up there. Okay, so it takes us 4 clock cycles to perform this transfer. Are there any questions about this? What do you think? Is this a Moore or a Mealy machine that I've illustrated? All right, clearly it's a Moore machine. I'm not going to explain why. Okay. The next step of our design principle is that we derive a state table for this state diagram, which is literally just writing out what the diagram indicates. There are 4 states, 4 present states that we have there, A, B, C, and D. A is the idle state. B is the state in which we set up the first transfer. C is the state where we set up the second transfer. And D is the state where we set up the third transfer. And so the next states are clearly indicated, and irrespective of W, whether W0 or 1 will go from state B to C, from state C to D, and from state D to state A, which is what this shows us. And the outputs that are asserted in each state is given by what's in the diagram as well. In state B, we have R2 out being asserted and R3 in being asserted. So that's these guys here. In state C, R1 out and R2 in, R1 out and R2 in, and finally in the last state, well, we want to transfer from register 3 into register 1, so we have R3 out and register 1 in, and we're finished. So when that transfer is completed, we will have been done, so that is asserted there. Right. Who's with me here and who's lost? Who's lost? Nobody. Right. Why are you lost?
I just completely blanked out as soon as you went through this slide.
Sorry? Blanking out when?
Yeah. As soon as you moved to this slide, I kind of blanked out. So I missed out the last 2 minutes.
Which slide?
Oh, the next slide.
This one?
Yeah.
Okay. Well, we haven't really discussed the slides yet.
Yeah.
Right. So after we derive the guy here, which is still symbolic and literally just a transcription of a directed graph into a table form. What we want to do is make a state assignment. In this case, we have 4 states, so how many state variables do we need? Log base 2 of 4 is 2. We'll need 2 state flip-flops that we can, where a particular valuation of those 2 flip-flops can be associated with each one of these states. The approach we're going to take is that we're going to do a sequential allocation. So state A is going to be given the valuation 0, 0 of the state flip-flops. State B is going to be given the valuation 0, 1, C is going to be 1, 0, and D is going to be 1, 1. So that's what's been done here in this table. The rest of the state table is the outputs are just transcribed immediately. What is important at this stage to do correctly is that the next state is transcribed correctly as well. So where we had A previously, we need to write 0, 0. Where we had B previously, we have to write 0, 1. Where we had C previously, we have to write 1, 0. Where we had D, we've got to write 1, 1, and here's AA for the last state, right? So that's how the state assigned table is derived from the state table. But that's not quite there yet. We want to then figure out, well, what's the logic that we need to derive the next state equations and the output logic that we need. So we see in our state assigned table or state table, we have these columns for the next state. They're labelled capital Y1 and capital Y2 for the state variables. They take on different values in different rows for a given present state and a given input, right? In this case, we have 3 variables we're dealing with. We have the 2 state variables, Y1 and Y2, as well as the input variable, W. So we have a 3 variable system, and we want to figure out, well, what's the equation that gives us capital Y1 in terms of lowercase y2, y1, and w. And that's given here in this Carnot map, which transcribes the right 0, the right 1 into the first column, the 0, 0 into the second column, the 1, 1 that you see into the rightmost column, and the 0, 0 into the second but rightmost column. And then simplifying this Carnot map, whereby we can see we have W as 1 and Y1 being 0, so not Y1 as this aqua term, and the rightmost column here is where we have lowercase y2 and not y1, which is that guy there. Playing a similar game with capital Y2 to derive the equation, the expression for the next state of Y2. We see the 0, 0 from the left columns of the first row here going into the first column of our Carnot map. Then 1, 1 going into the next column. The 1, 1 below that goes into the rightmost column because that's the column that's labelled Y2 is 1 and Y1 is 0, corresponding to this valuation. And finally we have 0, 0 going into this column here. And we can thereby see that capital Y2 is not Y2, Y1, which is this left column here, or Y2, not Y1, which is the rightmost column. And as for the outputs, well, they're going to be asserted for given combinations of the state variables given by the state in which they're asserted. We see here that in state B, which has the valuation not Y2 and Y1, we're asserting R2 out and R3 in. y2 out and R3 in are asserted when we have not y2 and y1. Similarly, R1 out and R2 in are asserted when we have y2 and not y1, and R1 in, R3 out and done are asserted when we have y2, y1. Right, so that's those expressions that we have here. And that then allows us to structurally implement this circuit, because it would look like this when it's implemented. We have our two flip-flops, which are given by the state variables y1 and y2. We have the logic expressions that determine what the next state is of these two flip-flops, the capital Y1 input and the capital Y2 input. And of course we have the output expressions, or the output signals that are asserted given these combinations of the present state. So you see here that you have overall a cost of 6 to input lookup tables. There's 6 gates there, 6 to input gates, and 2 flip-flops. Right. I wanted to ask you which of these gates are involved in next state equation derivation? So the gates that are numbered 1 through 6, which ones are involved in determining the next state? So if we think back to our model that we had early on, this one.
Yep.
So might not be that one so well as that's also not so great. There's, do we have a generic? I think there that's probably the nicest one there. We have next state logic that derives what the next state is, and we have present state given by the output of the flip-flops, and output logic that determines what the output of the system is. And of course we may or may not have a red wire that connects the input with the output logic as well, in which case it's a Mealy machine, right? So in our case, we have where are we? Whoop, that's not it. That's it. Which gates are involved in next state derivation?
1, 4, 3, and 5.
Any others?
2 and 6 go straight just to, the outputs.
There is actually a block
Oh,
there.
yeah, okay.
So
then
2 actually is involved in the input as well, or the next state equations. So 6 is only involved in output expression, right? These outputs. What other gates are involved in output expressions?
2, and then also 3.
Yes, 2 and 3, correct. And so which gates, is this a Moore or a Mealy machine based on the input-output logic relationship? So W only inputs into gate 1, which then feeds into gate 4, right? And neither gate 1 nor 4 is involved in output derivation, therefore we see no connection between W and the output directly. Right, so this is a Moore machine, not a Mealy machine. Okay. Now, we looked at a particular valuation, how we associated a particular value of the state variables with our states previously, where we had C being 1, 0 and D being 1, 1. grey encoding instead, where each state differs from the previous one in only one bit, which is achieved by flipping the valuations associated with C and D, then that changes this part of the table as well, and it clearly changes the K-maps. The K-map for Y2 is then much simpler, as you can see. The K-map for Y1 isn't any simpler than it was before. It's slightly different, but it's effectively the same shape. But then we have this not Y2, Y1 combination, Y2, Y1, Y2, not Y1. So we have 3 two-input gates here, plus this is a two-input gate. That's 4. This has to be a two-input gate. That's 5 two-input gates. So we save 1 two-input gate over what we had before. Slightly more efficient. Another alternative that's commonly seen is to use a one-hot status on. I told you already that this is by default what your CAD tool is going to be doing when you input a finite state machine and give it the freedom to choose what assignment to give to each of your state symbols. In this case, with 4 states, you have to have 4 flip-flops, and only one of them is ever active. So you go from the rightmost one being active to the next one, to the next one, to the leftmost one being active, and then you cycle around again effectively, based on the valuation that you're going to have in here, given that we wanted to go from A to A or B, from B to C, from C to D, and from D back to A again. Well then, if we treat all the other 12 possible, because that's only 4 choices out of the 16 possible combinations, treat all the others as don't cares. These are the expressions that we then get. So the rightmost flip-flop is asserted when W is 0, and we've already got Y1 being active, right, because we see it there and we see it here, or when Y4 is active, which is this case here. We see both, in both cases we have Y1 being active. Y2 is activated whenever Y1 is being activated, and we have W, whereas Y3 just follows immediately from Y2 and Y4 from Y3. So these expressions are much simpler. We have then 1, 2 two-input gates here, and a third two-input gate. So only 3 two-input gates now. So we have much simpler expressions as a consequence, and that usually means that the circuit can run faster. In this case, it's not going to be dramatically faster. Well, it's not going to be any faster than what we had before, because we still have the same shape here for Y1 effectively. All right. Now we looked at the more finite state machine. What about the merely finite state machine for swapping these 2 registers? So it's the same problem where we want to do 3 register transfers, but in this case we do the first register transfer, or rather set it up as soon as our trigger for the operation is detected. So when W goes 1 in the reset state A, we assert R2 out, and R3 in. So that when the next active clock edge comes along, with W being 1, when we enter state B, the first transfer will have already been done, because we set those control signals up as soon as we detected W as 1. This is possible in the Moore machine, because in the Moore machine, outputs are determined by the present state as well as the input. Whereas in, Mealy machine, outputs are determined by the present state as well as the input. Whereas in the Moore machine, we can only the state tells us what output should be active. So we had to wait until we entered state B before we could activate these outputs. But in the Mealy machine, we can do it immediately. We can do it as soon as we see that W is 1. in state B, so after we've already completed the first transfer, it doesn't matter what W is, we're going to set up the second transfer and complete it when we enter state C on the next active clock edge. And from state C, we set up the third transfer to be done, as well as asserting the done flag before returning back to our initial state, our resting state, our reset state A. So the advantage here of the Mealy machine is that we start the transfers 1 clock cycle earlier, and we also finish 1 clock cycle earlier, so it only takes us 3 clock cycles to perform the swap, as opposed to 4, as it took with the Moore machine. Right? Is that clear? But given that we've got 3 flip-flops, 3 states, we still need at least 2 flip-flops to store the state variables, right? We can't get away with just one. Are there any questions about this? So, okay. From where I'm standing, it doesn't look like you are getting it necessarily, that you're also not asking questions about it, and that worries me. You're meant to be mature adults and be able to ask questions if you don't understand something or if something is not clear to you. Okay? If it is clear, then that's great, but if it's not, you need to ask questions about it. Right? So I have no indication from you whether you understood it or not. All I see is blank faces. I know you do. Got that. I'm worried about the rest of the classroom. Well, there's many of them. That's the perspective that I have. And I assume my colleagues would have if they're teaching you as well, and you also don't ask questions or are not acknowledging that you understood it or not. If you just sit there with a blank face, we can't know. I can ignore that and just keep on going. It's not going to help you though. I think we might leave this because I'm not sure that I'm getting through to you at the moment. And this is just going to be another big example which perhaps has no value if you're not getting it. I know one person's going to get it, but I'm worried about the rest of you. Can you tell me anything? Give me anything to tell me whether you're getting it or not. All right, we'll leave it at that. We'll continue this after the quiz, I think. There's no point in going on if there's not enough indication that it's been understood. All right, so enjoy your week off. Would be, I hope that you have a somewhat, you think about how you're learning and what can be done to give your lecturer a better idea of whether you're understanding it or not.
I had a question about the
Yeah.
example it's from. It was from Shannon's expansion earlier with, I believe it sort of acted like what's it called? I think X and OR gate. It was like you had the lookup table that had, what do you call it, the cofactor that was going into it, and one of the cofactors was, the bottom one was a complement, and so it eliminated it.
Yeah.
It just treated it as a mux with the bottom 1 to 0.
Yes.
I don't understand how you can then put the bottom 1 to 0.
So this was one of the slides, was it? I think it is at the end of the lecture. Let me bring it up.
And also, I assume with that, the serial adder, it's just going to be 2 buses that make the register. The clock reads, like allows it to read and write from both buses, and then it adds with like a full adder.
Yeah, it doesn't. True, it doesn't use buses because it's all point-to-point connections.
Yeah.
But yeah, the idea is the same.
Okay.
Right, let me just go back. So this is presumably back in lecture 4.
Yeah.
And it's one of these. Oh, is it this one here?
Yeah. Yeah.
All
That seems
right.
like it could be useful.
Okay, so. This is the function, right?
Yep.
And this is one of those cases. You've got a four variable function.
Yep.
You need at most three input lookup tables
Yep.
to solve it, because this guy on the right will always implement a 2-to-1
The
lookup
variable.
table, and if one of the variables used to select this guy, then the other 3 variables
Yep.
are free to be used as inputs
Yeah,
to the other 2
so-
cofactors.
Yeah, so the 2 are different because by, like, at default, the 2 cofactors are going to have
Well, they
different
can be,
expressions.
they can be general. They don't have to be related at all.
Yep.
In this case, it happens.
Yep.
So this is our expression.
Yep.
I think it's worth noting here that the first term doesn't involve W1. The second one involves all 3. The third one doesn't involve W1, but the first one and second one don't involve W4,
Yep.
right? And the last one doesn't involve W3,
Yep.
right? So trying to find a maximal cover for those terms, it seems that W2 does appear in all of them.
Yep.
Neither W1, W3 or W4 appears in all of the other terms.
Yep.
So that to me suggests W2 is probably the variable you want to expand around.
Yeah.
So here it's shown what happens if you do expand around W1. So because W1 isn't explicitly referred to in this term, you have to expand it with W1 or not W1.
Yeah, for the
And therefore it's going to appear in both cofactors,
Yeah.
right?
Yep.
This one, it'll be in the cofactor with respect to W1 bar, W2, W3 bar.
Yep.
This one has to be in both again.
Yep.
And this one will only be in the cofactor with
Yeah.
respect to W1. So hence you get W2 bar, W3, W2, W3 bar,
Yep.
and W2, W3 bar, W4. And then we see that W2, W3 bar appears in both of these terms.
Yep.
So the W4 is immaterial.
Yeah.
You've got to have W2, W3 bar,
Yeah.
right? So it's W2, W3 outside of 1 or W4.
Yeah.
So that just becomes W2, W3. As for the W1 cofactor, yes, W2 bar W3. It's not going to have that guy. It's going to have this guy, W2, W3 bar W4, and it is going to have this last guy as well, W2, W4 bar,
Yep.
right? Anyway, there's no direct relationship between the two, so we're going to have to implement both of those lookup tables to implement both cofactors,
Yep.
right? However, if we expand around W2, then you do get this simplification, because then the cofactor with respect to W2 bar has W3, it has W1, W4 bar. So
Yep.
W3 or W1, W4 bar.
Yep.
And the cofactor with respect to W2 is W1 bar, W3 bar,
Mhm.
W3 bar, W4, and that's it, okay?
Yep.
And again, we see, just as we had in our example, that
The
these are complements of each other,
Yes.
right? Which means that it doesn't matter which one you take, but you can eliminate one of those. In
Yep.
this case, we took the cofactor with respect to W2, we implemented that one, which means this guy falls out, right?
Right.
And we've used 0, the most significant bit of the three input lookup table,
Yep.
as the, well, it's just not connected.
Yeah.
So what do you want to know? Do you want to know?
How you can just then eliminate the opposing cofactor and just replace it with 0. Like, I can't really get that image in
Okay.
my head.
Right. So effectively, when W2 is 0,
Yep.
then we want whatever is output by this guy
Yep.
to be F.
Yeah.
Right? So we're going to have in the truth table, when W2 is 0, we want F of W2 bar being the output of F. This is
Yeah.
W2.
Yep.
And when W2 is 1, we want the complement, effectively F of
W2.
W2,
Yes.
but that happens to be the complement of F of W2 bar, right?
Right.
So if this guy is 0, we want to output 0. If this guy is 1, we want to output 1,
Yeah.
right? If this guy is 0 here,
Yep.
we want to output 1 actually.
Yeah.
So 0 becomes a 1. And this guy, if it's 1, we want to output a 0.
Yeah.
So effectively, the truth table is pretty straightforward. You've got the 0 input, so we only really need four rows here. We've got W2, which can be 0, 0, or 1, 1, and we've got F of W2, the cofactor of F with respect to W2, which is either 0 or 1 in each of those cases. And the output of the three input lookup table has to be 0 in this case, 1 in this case, but when this guy is 0, we want to output a 1.
Yes.
And when this guy is 1, we want to output a 0. So it's the exclusive OR that gets programmed
Okay.
into the three input lookup table there.
Right.
And,
Okay.
and it'd be this, you don't even have to worry about the 1 because that never occurs.
Yeah.
But it would be when you program the FPGA, it would have the bits for 1 as well, but it'd be the same.
Right. So.
But it doesn't matter, it can be anything.
Right. So because you can ignore the 1,
You can ignore
Y
1,
is
it's
0 into it.
never going to occur.
Okay. Due to the fact that they're complements.
No, due to
Sorry.
the fact that you've wired that input to 0.
Yeah. Okay.
So
yes.
you can never get a 1 there.
Yeah.
You're never going to have a 1, the 1 part of the truth table
Right.
occurring.
Okay. Yep. Get it.
Does that make more sense?
Yeah, that makes more sense. Awesome. Thank you.
All right. Good-o.
Yes.
Well, I hope it all makes sense when you're reviewing over the.
Yeah. Yeah, I think it will. I've been very busy, so I haven't had time to properly
Don't be
do the exercises.
There's quite a volume there, so
Oh, yeah, I'll get it done.
you've got to.
I'll get it done during the flow, it's chill.
Yeah, you've got to be prepared for that.
Should be done. Alright, thank you.